My name is María José Jiménez. I work for CIEMAT. CIEMAT is in Spanish national institution dedicated to research in energy and environment. And I work for Plataforma Solar de Almeria in the south of Spain that is belonging to CIEMAT and mainly dedicated to solar thermal application, research and testing. And my presentation today is about an experimental setup and measurements of a round-robin test box there at Plataforma Solar de Almeria, and an overview of the available data that you will have to practice the techniques that you will learn. And also, we are going to talk about some data analysis topics. Then, this is the organization that will have my presentation. And first, I am going to give an introduction. Then I am going to talk about the round-robin test box, mainly first about the building, then about the experiment setup, and afterwards about the data. And finally, I am going to talk about data analysis topics. So mainly my presentation, the main part of my presentation is the description of the data that you will have to try the tools and the techniques that you are going to learn along these webinars. So I am going to start with the introduction. Here you can see the case study that we are going to consider. It is, as I said before, it is the round-robin test box. It is a simplified building that was constructed in the framework of an international collaboration in the UNFT8 of the International Energy Agency. Here we see two issues of this building that are important to develop skills in data analysis and also to try and to validate methodologies for data analysis. It is very simple, and then we have a very accurate knowledge of the construction, so it is easy to check our results. And also we have a lot of data of this construction, so it is easy to check our results from very different data sets to check if our results are consistent. So these are two important issues of this device. I will go afterwards to more detail on the description of this device. Then I want to say something about the, why are we using this device? We are trying to learn dynamic techniques for identification of thermal properties of building components, of the building envelope. We are trying to obtain steady state and other parameters from dynamic tests. And these tests are important because we are able to obtain these intrinsic parameters from dynamic tests using our tools. And it is important that we are able to do this from test campaigns that are time varying and involve a lot of phenomena. in the test campaigns. So all the phenomena that you have learned before are involved in this test campaign. So in general, it is useful also to implement approximations in the data analysis. So it is important to know our physical system and to have very good knowledge of the physical phenomena, to have good criteria to make simplifications that are necessary to go ahead in the data analysis. Then it is also important to take into account that we are dealing with dynamic conditions, but we are looking usually for some constant parameters. So it is different to have a dynamic test with varying temperatures, heat flows, etc., and parameters that are something that can be considered intrinsic. So we are trying to extract these intrinsic parameters from our dynamic test. So this is the strength of our tools, of our methods. So then our tools and methods must be robust. So if we know from the physical knowledge that a parameter should be constant, our result should be constant even if we change the data series. Also, if our tools are strong enough, we should be able to identify dependencies if the phenomena are not characterized by constant parameter, or if they need a function, we should be able to identify the function. So we should be able also to use, to decide, to evaluate ourselves if the results are logical or not, taking into account common sense and the knowledge, the previous knowledge of the system that we are analyzing. So this is why it is important to use simple devices, simple case studies, because to start learning the tools for system identification, simple system allow us to analyze phenomena that are not simple themselves. For example, dynamic behavior is not simple, but if we study in a simple building, it's easier to learn. Also, the complex phenomena are present in our simple buildings, so it is useful. And also, this simplicity allows us to put the focus on the main step of the data analysis and also on the physical phenomena. So we don't have to worry about the complexity of the system. We have to pay our attention when we are starting to learn on the tools and the process and the step of the data analysis. Also, the previous knowledge gives us criteria to the validation of the results. And of course, the well-known characteristic of our system facilitate to identifying wrong results and check our analysis skills. So then this is why we are proposing using such simple system. Also, something that is important is that when you are starting to learn and you are starting to use the tools for system identifications, sometimes it is typical to obtain wrong results. Sometimes, not always, but sometimes you can obtain wrong results even when you consider candidate models that make sense from the physical point of view, and even though in a very simple case study. So this case study allows you to identify these problems and to identify why you are obtaining these wrong results. This simple case study also is useful to develop skills in validation and to decide to make decisions about detecting wrong result and rejecting, and also to develop awareness of the relevance of validation. Then, also, other thing that is very important is to have several data sets with different test conditions. Then you can identify if different data sets are giving you different results for a parameter that you know should be constant, then this is a criteria to reject the result. And also you can learn that some data could be not optimum. So the test conditions can help you to find more accurate results. So the accuracy of the results depends on the accuracy of the data, but also on the test conditions. So if you have data, like in this case, under very different test conditions, you can see how some of the data will give you more accurate results than others. Then, after this introduction, I am going to talk about the building, the simplified building that we are describing, that is the round-robin test box. This is the two pictures of the same building. It was tested in Belgium and also in Spain and also in the Basque Country, also in the Czech Republic and also in France. It was constructed in the framework of the Annex 58 of the International Energy Agency in an international collaboration framework to carry out research mainly dedicated to experiment and to data analysis. So the round-robin box was constructed in a country, and then it was sent around the world to different teams that carry out different tests and provide different data sets. It is relatively small. It is 1 cubic meter, mainly constructed by insulation. We have all the details of the construction, but in principle, we only use these details for validation. In principle, the characterization is done only based on data. So I said it's basically insulation, and also it has a wooden frame, a window with a wooden frame. So you can see here the two pictures. The first one is a test carried out in Belgium in winter, and the second one is a picture of the test carried out in summer in Spain. But in Spain, we had it for about 8 months. So we will distribute you the data and the description of the building and the experiment setup and the data from the experiment in Spain from winter, from 3 data sets. But you can know that in Spain we have more data with more different test conditions. This building has several possibilities for practicing with the tools that you are going to learn. One thing is to make the characterization of the walls. Then using the heat flux through the internal surface of the walls, you can obtain the thermal resistance or the U value of the walls. This is possible because the heat flux is placed in a homogeneous wall. If the wall is not homogeneous, then this is not possible. So we have heat flux in every interior wall of the building. So basically, if you are starting to learn these techniques, it's important to start from the very basic analysis and then increase the complexity. So if you have already played with the data from simulation, this is a step forward because this is reality, but it is still a very simple energy balance in a surface. What you need to use for the identification, is a one-dimensional heat flux, and it's very easy. So if in the process of learning, the identification of the parameters of the walls are very interesting and useful to develop skills. Then you have so many data. You have more data than the data that are necessary, but also you can use the energy balance in the whole volume inside the building envelope to obtain the heat transfer coefficient of the heat loss coefficient of the whole building envelope. So this is a more advanced system, even though we are talking about the same building and the same experiment setups. First, you can play with the walls, and then you can play with the whole volume. But in the two cases, the important thing is that the starting point should be the energy balance equations of each case. Then I also wanted to show you this because this is the place where we install the building for the experimental campaign. It is at Plataforma Solar de Almeria, where I work. I show you this view because you see the test facilities, the distances, and you also see that we have one main place for the testing on the right, but also we have several devices distributed in the place that can be used for checking the measurements that we are doing. So we have, for example, meteorological data in the place where we are doing the test, but we have two more meteorological stations for validation. And you have in the data file, you have the main data of the round robin box and also same data from the Meteo 1 and from data from Meteo 2. So this is a good thing because the experiment setup is oversized. So this is because we are doing testing, we are doing research, and it's very useful for checking validity of the measurements in general. It's very useful to have more data than the data that are necessary. Then you can make decisions yourself. Imagine that you need to do your own experiment. Then you should decide what to measure. In this case, you have many measures and you should decide what to use, but it's something similar. So it's important also to develop the capability to decide what is necessary to measure. So in this case, in the context of research and develop skills for analysis, You have here a collection of the sensors and devices that we have used. In this picture, you can see only the main devices. We have even more, but I am going to show you more in detail the devices in the next slides. First, from this picture, you see the general view. On the left, you see the wind speed sensor, the anemometer, 3-meter height. Then on the other side, on the right, you see a vertical pyranometer. This is not the only one vertical pyranometer. We have others in the same orientation that give us validity of the measurement. Also here you see the air temperature sensors that I will talk about them afterwards. And then more in detail, we have also the measuring devices for the solar radiation. As I said before, we have a very, very detailed collection of measurements of solar radiation. We have beam, horizontal, global, diffuse, and also we have long wave radiation. And also other that we don't have here in the picture is reflected. We have an albedometer, and we have the vertical facing north. All this information with the description is in the document that you are going to be able to download from the web page, and also the data. So the full description is in the document. And then with a bit more detail, I am going to show you the device that we have used for the measurement of the air temperature. How have we done this measurement? First, the indoor air temperature. We have protected the sensor from solar radiation with aluminum cylinder that allow ventilation. You can see on the left the position of these sensors. And also you can see on the right how is the protection device where the sensor is inside. This is for indoor air temperature. Then for air temperature, we have also two devices here, but we have more devices in the meteorological station. The devices here are with protected from solar radiation and using devices that allow natural ventilation. It's important, the device that we are using, because natural ventilation is promoted by solar radiation. The higher solar radiation, the higher natural ventilation. So ventilation is guaranteed in principle. Also, we have in the meteorological station nearby, we have also a sensor with a mechanical ventilation system that allow us to check that these sensors are valid. The measurement of this sensor are valid, are in very good agreement. Then also other thing that is important is to measure the temperature of the surface. Maybe you don't need to use it, but in case we need it to investigate, it should be as good as possible. And also the heat flux through the internal surface. These measurements have several issues in common. It is important to integrate very well the sensor in the surfaces, to be sure that the sensor is at the same temperature of the surface that they are measuring in the case of temperature, and that the heat flux through the sensor is the same heat flux through the surface where they are. So it is important to integrate very well the sensors in the surface. Even though we integrate very well the sensor, we could have some perturbations, but the idea is to minimize the perturbations as much as possible. So the idea is not to have a very accurate sensor. The idea is that the sensor gives accurate measurement. So a very accurate sensor, if it is not well integrated, if it is not well placed in the surface, it could give very bad measurement. So be careful with this. Also, it is important the contact, the integration, the contact with the surface, and also the optical properties to have try to make the sensor, the surface of the sensor with the same optical properties of the surface that they are measuring. And how we have done it, glowing the sensor in the surface, painting the sensor with the same color of the measured surface, or protecting the sensor with an adhesive tape with the same color of the surface. So you see here the final on the left you see the sensors, and on the right you see the final position. In the exterior, the surface is white, so we put a tape in white over the sensor, glue, very well glue. And also in the interior, we painted them in black because the surface is black. Also, these are the main issues about the measurements devices, but these are the most critical measurements that we have there. Also, we have other measurements that are also available to develop skills. So we have one heat flux sensor in each wall, in each in the interior, in each interior surface of each wall. We have a PT100 also in each interior surface. And also we have a distribution of thermocouple that give you the average of the surface temperature of each wall in the internal surface. So you can see the full description of the setup in the document, and you can use this information to develop your skills. So you can start with very simple analysis and try to make it more and more complex, and see what happened if you try to increase the accuracy of your model and see what is the behavior of the validation analysis. Then one thing afterwards, when you have the experiment set up, then the next step is to produce the data. To produce the data, then it is important to be sure that the test campaign guarantee that the data are useful for identification the thermal properties that you are looking for. It is important. One of the most important things is that the driving variable of each phenomena in the energy balance is high enough, is strong enough. And then this is because if we are doing an analysis, a data analysis based on an energy balance, then the energy balance has different terms. Each term is representing an effect, and each term is writing from a variable and a constant. Then the variable is what we measure. So the variable that represent each phenomena is called driving variable should be strong enough to be able to identify this phenomena. If it is not strong enough, we could have problems because the signal to noise will be poor and we have difficulties in the identification. In this case, probably it's better to ignore, assume that the effect is negligible. In the case of the phenomena is not strong enough, can be better even for the accuracy to disregard the phenomena. So if we want to identify a phenomena, we need that the driving variable is strong enough. For example, if we want to identify the heat transfer coefficient to the outdoors, the indoor to outdoor air temperature difference should be high enough. To identify the GA value, we need a strong solar radiation. And then if we want to identify dynamic properties of the heat capacity, we need a variability of the measurements. Also, one thing that is important is to have a good representation of the indoor air temperature. And homogeneity is also something that is necessary. In our case of the experiment that we are describing, we put inside the building a very, very small fan to move the air. But it is enough to move the air and avoid stratification, but it is very small because if it is too big, it could make a perturbation on the surface heat transfer coefficient. So this is why we have chosen a very, very small device to move the air with a very, very low power of ventilation. The data series that we have are described in this slide. We have described in the document 3 data series. For starting, is more useful the series number 16 and 17 because are supposed to be the optimum, and then we are increasing difficulty. So don't worry if you start, for example, with the last one, with series 18, and you obtain wrong results. Don't be frustrated because this series is provide to go ahead in research and to go ahead in the development of procedures in research. So series 16 and 17 are quite good to start and to learn and develop skills. Series 16 is optimized with a Rolls power sequence and it is optimized from the point of view of the dynamic test for the application of the identification techniques. And also series 17 was provided as a kind of co-heating test to have a reference for comparisons. In principle, we intend to have a kind of co-heating test, but taking into account the test condition and the boundary, the climatic conditions in the south of Spain, it was not possible to maintain the temperature to 25. So we set the set point in the indoor temperature to 35 degrees. And this series is intended to have a reference and also to investigate the capability of the dynamic techniques to identify the thermal parameters on this condition. So it can see from 2 points of view. And the other data series intend to go ahead in the reality, to have more conditions more close to reality. The 18 is trying to have a constant indoor air temperature that could be seen as typical from an in-use building, and other that are available and are not going to be supplied are incorporating infiltration, different orientation, phase change materials, etc. So these are the characteristic of the series. So in principle, to play and to start is important to have in mind the first two series. And afterwards, it is important to have a look to the data. I am going to show you, but as you learned in the previous presentation, it's important to have a look to the data and to analyze if you see some strange behavior. I am going to show you just to demonstrate a bit more the difference between the data series. You see in the three data series similar conditions of solar radiation in the test site, but the first one is according a dynamic series of heating according to a ROR sequence. The second one intends to have a constant indoor air temperature and the outdoor temperature that we have there in the test site in winter. And also last one, trying to have 21 degrees, but it's impossible because the solar radiation is so strong that produce overheating on the air when we set the temperature to 21. One important observation here, as I said before, it's important to have to identify the heat loss coefficient. It is important to have a large high delta T difference between indoor and outdoor air temperature. As you see in this picture, the one with the larger difference of temperature is series 17. So in principle, it should be better to identify this property. However, the series 18, as we expect, is worse regarding this difference of temperature. And also the first one has a more dynamic behavior in the indoor air temperature and also in the heating power. So this is more useful because also the heating power is contributing to correlate the solar radiation and the indoor air temperature. So it's something that is good, even though the delta T is a bit smaller than in series 17. So these are the graphical differences that you can observe that are leading to different behavior regarding the accuracy of the result. So it's not only the measurements, it's not only the quality of the sensor, it's important the location, the installation, the proper installation, but also the test condition, the sequence that we carry out for the test. But anyway, we are doing research trying to get good results from not so optimum tests. But for a start, it is good to fix in the first two kind of test conditions. Also, that is interesting to observe and to discuss is the behavior of the surface temperature. You see that the external surface is affected by the solar radiation, probably also the sensors, even though we have tried to integrate very well. And you see in the indoor surface different behavior from the sensors that are at the back and on the floor and the ceiling. We will see in the next slides why we have this different behavior. In principle, we have similar behavior, but we have some peaks in the floor and the left and right walls. And finally, I am going to go to talk about some analysis topics. I am not going in detail in the different techniques. I want to just to mention some hints that are important when you are modeling, combining the information of the sensor, the information of the measurements, the information of the test campaigns, and also the capabilities of your tools. I am not going to go in detail in the tools on the techniques for system identification because there are other webinars dedicated to this. So I am just going fast and trying to make the relation between all the topics. System identification is a very multidisciplinary task, so it's important that you take everything into account. So it's important that you take into account all the knowledge that you already have, everything that you are learning, and then when you go to a very sophisticated tool, don't forget about this, because the sophisticated tools don't solve the problems that you have learned to solve in the process. So if you combine all the knowledge that you are acquiring with a very sophisticated tool, probably you will be very good in doing data analysis. But don't forget about this. Physics is important. Everything you know about the measurement, test campaign, test setup is also important. So I am going to talk a bit about the qualitative data analysis and pre-processing, and also about constructing models from measured data. Then, for example, when you are playing with system identification, it's important that you propose several candidate models. Sometimes you obtain wrong results from models that in principle could be logical. For example, think about solar radiation on the opaque walls. And if you look at the data of the measurements in the surface, you should think if this measurement, in general, if any measurement makes sense. But for example, do I need to include the solar radiation in the models of the opaque walls? If we are looking for the thermal resistance, or we are looking for the U value? It's a good question. It's not evident. Maybe yes, maybe not. Maybe yes in a kind of wall, maybe not in other kind of wall. Then other issue that is important is the position of the sun. In summer, for example, in Spain, probably the sun is affecting only the direct solar radiation is affecting only the external surface because the position. But in winter, we have solar radiation through the window that is incident on the floor and on the right and left walls. So you have an increase of temperature and increase of flux that could be because radiation or could be because a perturbation in the sensor, even though we have tried to avoid difference in the behavior of sensor and surfaces. So it's important to make an interpretation of the measurements that you have before starting to write a model, before starting to propose candidate models. In the case of summer, we don't have this problem of solar radiation through the window because it is just diffuse. So we have to worry only about this incident solar radiation on the walls. This also is the problem that we have on the roof and also on the back wall. So if you are starting to learn to use these tools and to do system identification, it's good to start with opaque walls, just with a one-dimensional analysis, and start, for example, with the back wall that receive only very little solar radiation and also is measured with a pyranometer here. So you can discuss if the solar radiation incidence on the back wall is relevant or not for your analysis. Also, you can discuss if the solar radiation is relevant or not on the ceiling. So this kind of observation are important. Before the modeling, maybe interesting proposing model with and without solar radiation if you have the measurement and compare to make conclusion about the suitability and the relevance of including the solar radiation on your model to obtain the U value and to obtain your thermal resistance. So it makes sense. Candidate models with and without solar radiation. But this is just an example of what can you see, what decisions can you make just looking at the data. Just looking at the data, you can take ideas on what should be the most suitable candidate models. Then other issue that is important is averaging and filtering. Averaging and filtering is very useful sometimes it's not necessary, but it's important that when you apply these techniques that are being discussed in other presentation, it's important that when you apply this, you are sure that what are you doing? What is the effect? It's important that when you apply a filtering technique, you don't remove relevant information from the data. For example, you have here two different records. One is about heating power, and the other one is about temperature. If you do filtering of, you have sampling of 1 minute, and then you carry out sampling of 10 minutes, you see that it's not very relevant, the difference. So we could accept this filtering technique, and is also useful because it seems that it removes some noise information that is not corresponding to your phenomena. But if, for example, you do, in this case, an average of 60, then on the left, you see that the information is totally, the shape of the curve of the heating power is totally different. It isn't relevant to the indoor air temperature, but however, in the of the heating power that we have established to produce a dynamics series for improve the capabilities of the system identifications, if we apply this filtering, we are destroying the information of the data. Here you can see a bit more in detail what happened. If you have the red curve that was established to facilitate the identification with on-off, if you carry out a wrong filter, you eliminate the dynamic behavior, so you destroy the information that you have produced for improving the identification process. So this is something that is important. In general, also, what I said before is an example on how far is important in the step of filtering, and also the knowledge of the physics is important in all the approaches for data analysis. I am going just to mention, we will go back to this information afterwards in other seminars and also in the summer school this year, but it's important that you construct candidate models based on the physics or your system. And sometimes it's necessary to apply approximation. Approximations are always necessary. So when it is not clear for you qualitative from the qualitative point of view what is the best approximation, then you can produce several candidate models and you can analyze and check the validity of the results, and then you base your decision of the results on this validation process. So always the physics is always necessary to construct the candidate models in all the approaches that you are going to see. Have here a collection of key ideas that are important for the construction of the candidate models that are relevant for all the approaches. What is the system that you are going to study? Are you going to refer the energy balance equation to the volume inside the building envelope, or is in a flat surface regarding the heat flux through it? You must know the phenomena theoretically in your energy balance equation, but also it's important to identify what are the more relevant phenomena, because it is quite impossible to do a full model work with all the phenomena. What is more efficient to model each phenomena? The phenomena can be simplified, so it is good to simplify, to avoid time, to avoid energy, to avoid money also in the measurement. So this is also important. Which are the main driving variables? It's important to know which are the main driving variables to write down the contribution of the energy balance, and also causality, to decide which is the input and which is the output. There are many possibilities to choose inputs and outputs in the models, but your knowledge of the system must help you to decide what is more appropriate. And then, as I said before, if you are not able to identify all the optimum approximation, it's good to assume and to study several candidate models. Then I am not going to insist more in this. It's important, as I said at the beginning, you can apply an energy balance equation in an air volume or in an interior surface. In all the approaches, you can apply many different approaches, but it is not just taking a model from somewhere and put your data and obtain an, let's say, U-value. It's important that the model is adapted to the knowledge of your physical system before putting this model in the tool. And also in the energy balance equation, it's important to identify the driving variables. Here you have an example with column the energy balance term, and in other column the driving variables. This is just an example. It's something that you must done in every example that you are analyzing. let's say, for example, in the RC models, then you have an electrical analogy, but you can make a lot of decisions, how many nodes you have, depending on the thermal mass, how many branches you have. If you have a fast conduction, it's good to have a parallel branch with a more slow conduction part that could represent the fast one, the windows or air infiltration, and the slow one, the walls, the opaque walls with insulation, etc. This is the case of RC models. It's not just put an arbitrary electrical model to represent your system. Is something more. It's a translation of the knowledge that you have about the system, about your building, to an electrical analogy. Here, there are two examples of two different kind of circuit that could be used. In the first case is a monodimensional analysis of opaque wall. In the second case is a three-dimensional analysis of whole building. And you can study how many nodes do you need, which is the output. Steady state analysis, even steady state analysis can be optimized with physical knowledge, etc. And well, here I am not going to go more in detail of this, just to tell you that even steady state approaches can be optimized, taking into account the physics. Some publications where you can go in deep on this, but for starting, I think it is by now this is not necessary to start with system identification. Just have in mind that we can do many things with physics and the different approaches, even other models, for example, arcs. You need an energy balance equation of the steady state to compare with an ARCS model to obtain proper parameters. Otherwise, the parameters don't make sense. So it's important, even in these approaches that are traditionally known as black box approaches. Even in these approaches, it's important to take into account the physics to write the correct energy balance equation to compare with the ARC models, and also to define inputs and outputs. And some papers also. And finally, in stochastic space models also, this is very, very flexible. In the next week, you will learn about CTSM that give you a lot of flexibility writing down equations. So it's important that you use the flexibility. Don't be just using a given model. You must construct your own model with your knowledge, and then probably you will get very good results. We already talked in the previous seminar about model validation. I want to insist also in model validation, physics must be present regarding the common sense and the information we have previously from the system. For example, I said at the beginning, if you know that a parameter, you should obtain constant parameter changing the data. Then if you are not obtaining such repetitivity, probably your approach is wrong. And also, you will see in the next seminar more about the interpretation of the residuals. Also be careful, because the interpretation of the residuals are typically correlated to solar radiation. This is a problem with the modeling of solar radiation, but maybe many other things related to solar radiation. For example, infiltrations, if the air leakage is not well modeled, if the air leakage depends on the wind speed, and wind speed depends on the solar radiation, finally you have a problem due to the air leakage that is seen in your residual as a 25 hours residual. But in principle, okay, it's related to solar radiation, but there are many, many other things that could have correlation with the solar radiation and the 20 produce residuals with 20 hours frequency. And in general, frequent mistake is obvious if you ignore of the hints that are important in construction, the models, the candidate models you will have from results. So if you have results that are absurd, go to the beginning, to the experiment setup, maybe to the quality of data, to the sequence of the test, to the test conditions, to the candidate models, to the approximation that you have done, etc. To the, for example, to the assignment of inputs and outputs. There are many things in these steps that could give you very bad results with very good data and very sophisticated tool. So the message, the final message is pay attention to all the steps in modeling, in system identification, in experimental assessment of thermal performance of building and building components. It's not only using very sophisticated tools, it's not only being very good in statistics, it's a combination of many things that give you good results in a multidisciplinary framework. So this is all from my side. You can have more information in these documents that I reference here. And then you can download the documents from the links in this slide, also to the data in this link, and also to the document describing the data and the 3 data sets that I have described. So sorry, because I was a bit late, and I am available for you for question. If not possible today, then you can send me and I answer, or I can answer you in the last webinar in September, by the end of September, the 13th.